Welcome to Tomorrow Unveiled.
It's great to be back.
We really need to talk about the week of February 5th to February 12th, 2026. I've been looking through all the data our dedicated research team pulled together for today, and I'm honestly struggling to find a parallel. It wasn't just a busy week. It was, I don't know, it feels fundamentally heavy.
Heavy is definitely the right word. I mean, just in terms of pure physical tonnage launched to orbit. But economically, I'd probably call it high beta.
High beta, okay, so in finance, that's a term for high volatility, right?
Yeah.
High risk, but high potential reward. A stock that just moves way faster than the market.
Precisely. For the last, 10 years? We've been in this new space era, lots of startups, lots of impressive prototypes, and let's be honest, a lot of PowerPoint presentations about future capabilities.
A lot of promises.
A lot of promises. But this week felt different. The volatility wasn't about promises on a slide deck. It was about massive, tangible infrastructure actually hitting the vacuum of space. We saw this huge realignment of the whole industry.
It really does feel like a graduation ceremony of sorts. We're not just watching rockets go up as a novelty anymore. I mean, the research team pulled filings on orbital data centers, which I still can't quite get my head around that being a real proposal. And then there's biological hacks for keeping astronauts from aging in space, and just the traffic jam that's building up in low Earth orbit.
It's a convergence. And that's really the mission for us today on Tomorrow Unveiled. We need to unpack how all these different threads, heavy lift capacity, orbital computing, even biotechnology, are all smashing into each other in the exact same 168-hour window.
And we have the documentation to prove it's not just hype. We've got the flight logs, the FCC filings, the scientific journals.
And of course, you have to look at the forums, the Reddit threads, where the engineers who actually build this stuff sometimes leak the real story.
Right. The flight logs tell us what happened, but the filings tell us where the money is going.
And that's always where the real story is. Follow the money.
Then let's do it. Let's follow the money and the rocket exhaust. Segment 1, the heavy lifters. If you think about space as this emerging economy, then the rockets are the shipping fleet. And for a while there, it really felt like Europe was stuck with a rowboat while SpaceX was running a fleet of supertankers.
That's a good analogy. And that's exactly what changed this week.
So this changed on February 12th.
It did, February 12th. The Ariane 6, and specifically the 64 configuration, finally had its debut launch. And you can't overstate this. For the European Space Agency, for Arianespace, this was a truly existential moment.
Okay, unpack existential for me. Was the program actually on the chopping block?
Oh, without a doubt. Europe's been in what many are calling a launcher crisis. They retired the incredibly reliable Ariane 5. The newer Vega C rocket had a string of failures.
And they lost access to the Russian Soyuz rockets.
Exactly. Yeah. Geopolitics completely cut off that option a few years back. So they ended up in this incredibly ironic position of having to pay SpaceX, their #1 direct competitor, just to launch their own critical satellites. This launch was about regaining sovereignty. It was about being able to get their own stuff to space on their own terms.
So the 64 configuration, let's get into the specifics. The 4 refers to the number of solid rocket boosters strapped to the side, right?
That's correct. There's an Ariane 62 with 2 boosters, and this one, the 64, with 4. Now, it sounds like a simple change. You just strap on 2 more solids. But in terms of performance, it's a massive leap. It effectively doubles the lift capacity to low Earth orbit.
How much are we talking?
We're talking about 21.6 metric tons. That single change transforms the rocket from, a capable medium lifter into a true heavy lifter. It puts them back in the game.
And for this crucial first flight, they didn't just send up a dummy payload, a block of concrete like they used to.
No, absolutely not. They sent up Amazon.
32 Amazon Project Kuiper satellites.
And that's the beautiful irony of the modern space industry, isn't it? Amazon is building out this massive constellation specifically to compete with SpaceX's Starlink. But to get their satellites launched, they need rockets that aren't SpaceX.
So they're a key customer for Arianespace.
A lifeline customer. They've already booked 18 of these Ariane 6 launches. So this flight wasn't just a one-off test. It was the start of a real industrial cadence. They need to fly these things regularly.
That is an enormous backlog to start with. But looking through the specs our researchers pulled, something that stood out to me was the fairing size. It says here a 20-meter tall nose cone.
It's cavernous. I mean, you could practically fit a small apartment building inside that thing. And that volume is becoming just as important as the mass.
Why is that?
Well, for a while, the trend was all about CubeSats, these tiny shoebox-sized satellites. But the pendulum is swinging back. For serious power generation, you need large solar arrays. For high-throughput communications, you need large antennas. The physics demands volume. Ariane 6 is designed to offer that.
But the real technical achievement here, it wasn't just the successful launch, was it? It was also about what happened after the payload was deployed.
Exactly.
It didn't just leave the upper stage up there as junk.
Right. The upper stage has what's called the Vinci engine, and the key feature is that it's reignitable. So after it dropped off all the Amazon satellites at their target orbit of 465 kilometers, it fired its engine one last time.
To push itself back towards Earth.
To push itself into a decaying orbit where it would burn up completely in the atmosphere. It's responsible spacekeeping.
Which is absolutely crucial, and we're going to talk a lot more about that later because orbit is getting dangerously crowded. But okay, so while Europe was celebrating getting back in the heavy lift game with a more, let's say, a traditional expendable rocket.
Albeit a very modern and capable one.
Right. But at the same time, China was doing something that feels, well, it feels like it's a step further ahead.
They're playing a different game entirely. Europe was solving for capacity. China, on February 11th, was solving for reusability and human rating. We saw a critical test of their Long March 10A rocket and the new Mengzhu spacecraft.
People were calling this China's Falcon 9 moment.
It's a tempting comparison, but it's actually more specific than that. It's all tied to their lunar ambitions. What they did was a hop test with the first stage. They launched it, flew it to a certain altitude, restarted the engines in flight.
And then performed a controlled splashdown. I wanted to ask about that, a splashdown.
In the ocean, SpaceX is landing on concrete pads or drone ships. Why go for the water?
It's a safety margin for now. Landing in the ocean is just. It's safer for the early tests when things are more likely to go wrong. But the physics of what they accomplished is identical to a land-based landing. You still have to restart a complex engine while you're falling backwards at supersonic speeds.
You have to deal with the fuel sloshing around in the tanks. All the fluid dynamics, exactly. And you have to steer with grid fins. They prove they have the guidance, navigation, and control software nailed down. The landing part, whether it's on a ship or in the water, is the easier part of the problem, relatively speaking.
But the part of this test that was, I don't know, either thrilling or terrifying, depending on how you look at it, was the test of the capsule, the Max-Q abort.
Yes. This is the kind of test that gives engineers nightmares. They usually only simulate this on computers.
So break down Max-Q for us. What is it?
Max-Q stands for maximum dynamic pressure. It's the precise moment during a launch when the combination of the rocket speed and the air density creates the maximum physical stress on the vehicle's frame. It's the point where the rocket is most likely to break apart.
And they decided that was the perfect moment to pull the emergency ripcord.
Intentionally. They fired the launch escape system at the most violent, dangerous millisecond of the entire flight. The escape tower rockets have to fire with enough force to pull the crew capsule away from the exploding rocket faster than the rocket itself is accelerating.
It's like an ejection seat in a fighter jet, but you're doing it at Mach 1 while you're literally strapped to a skyscraper-sized controlled explosion.
That's a perfect way to put it. And the fact that they nailed both the booster recovery logic and this critical human safety abort test in the same week,
Yeah.
it's a massive signal. It tells the world that the Long March 10 isn't just a paper rocket anymore.
This is the hardware.
This is the hardware they plan to use to put Chinese taikonauts on the moon by 2030. They are validating their human safety margins, and they're doing it in public.
Okay, so we have Europe securing its heavy lift capability and China securing its reusable, human-rated future. And then we have the United States, or more specifically, the United Launch Alliance, ULA, and their new Vulcan rocket.
The new workhorse. This was mission USSF-87 for the Space Force. A classified payload, of course, so a very hush-hush trajectory.
But the launch itself wasn't entirely so quiet. There was a little bit of drama. Our research notes here keep mentioning an observation.
Ah, yes. The delightful euphemisms of the aerospace industry. It's the only field where words like anomaly, excursion, and observation are used to describe what are essentially explosions or major structural failures.
So what exactly was this observation?
If you watch the launch footage very closely, and believe me, the online space community has dissected this frame by frame, it appears that the nozzle on one of the solid rocket motors, the SRBs, failed.
Failed how?
It looks like it liberated itself,
Oh.
which is the polite engineering term for it broke off and fell into the ocean.
That sounds bad. I mean, catastrophic even. If you lose the nozzle, don't you lose your ability to direct the thrust?
Normally, yes, it's a recipe for disaster. You get what's called asymmetrical thrust, which can send the rocket spinning out of control. The nozzle's job is to focus all that energy. Without it, the thrust just spills out in all directions or loses a ton of efficiency.
But it didn't spin out of control.
It didn't. And this is actually a huge testament to the flight control software on the Vulcan. The main BE-4 engines gimbaled, they swiveled, extremely hard to counteract the rogue torque from that bad booster.
The rocket's brain saved it from its own muscle failing.
It saved itself, and it delivered the payload to a perfect orbit. The mission was a success. But for a customer like the Space Force, this kind of event falls into the cone of uncertainty.
What do you mean by that?
ULA's entire business model is built on being the premium, high-reliability provider. You pay more for a ULA launch because you absolutely, positively cannot afford for it to fail. Now, 2 out of their first 3 Vulcan flights have had issues with these solid rocket motors.
So it proves that even old space, with all its heritage and experience, isn't immune to this high beta volatility we're talking about.
Physics doesn't care about your company's legacy. But if you step back and look at the aggregate picture, Europe, China, and the USA, all flying massive new hardware in a single 7-day window, the global capacity to lift things to space just took a massive step up.
The highway to orbit is getting a lot wider.
A whole lot wider.
And before we get into what this means for the absolute traffic jam that this wider highway is about to create, we just have a quick request for everyone listening. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners.
And for our YouTube viewers, if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
Okay, so we've established we now have the giant dump trucks to haul stuff to orbit. Now let's talk about the cargo. And this is the part of the research where my jaw just kind of hit the floor. We've all heard of Starlink. We get the idea of internet from space. But SpaceX filed a proposal this week that it changes the entire game.
The Orbital Data Center filing.
They are talking about putting 1 million satellites into orbit.
It sounds like a typo, doesn't it? I had to read the source material our team compiled 3 or 4 times to make sure I wasn't misreading it. But no, up to 1 million units, orbiting at altitudes between 500 and 2,000 kilometers.
My first question is just, why? I understand beaming internet down, but why put the actual computer servers in space? My laptop gets hot enough sitting on my desk. Surely a vacuum is the absolute worst place to try and cool a massive data center.
That's a really common misconception, actually. It's counterintuitive. In a vacuum, you're right, you can't use fans. There's no air for convection, which is how we cool almost everything on Earth. You can't just blow air over a heatsink.
How do you do it?
You use radiation. If you have large enough radiator panels and you design the spacecraft to keep them pointed away from the sun and the Earth, then deep space is a functionally infinite heatsink. It's sitting at about 3 Kelvin. That's near absolute zero. You can radiate all that waste heat away very, very efficiently if you design the system correctly.
Okay, so cooling is a solvable engineering problem. What's the business case? Why go to all this trouble?
Our research team identified 3 main drivers in the filings: energy, latency, and sovereignty.
Let's start with energy.
Data centers on Earth are becoming an existential threat to power grids. The amount of electricity needed for AI training runs is staggering. We're literally reopening old coal and nuclear plants just to feed them.
Right.
In orbit, if you place your satellites in what's called a dawn-dusk orbit, a specific path that basically rides the terminator line between day and night on Earth, you can have 247 uninterrupted solar power. No clouds, no nighttime.
It's infinite clean energy for your server.
Exactly. The second point is latency, the speed of light. Light actually travels about 40% faster in the vacuum of space than it does through a fiber optic glass cable. The glass itself actually slows the photons down.
I never thought about that.
So if you're a high-frequency trader trying to bounce data between the stock exchanges in London and New York, a laser link between satellites in space is physically faster than the undersea fiber optic cable. For some applications, those milliseconds are worth billions of dollars.
Okay, energy and speed. And the third one, sovereignty. This sounds interesting.
This is where it gets a little cyberpunk.
Right.
If your data is being processed on a server sitting in a data center in Virginia, it's subject to U.S. law. The FBI can subpoena it. If it's in a data center in Frankfurt, it's subject to EU's GDPR regulations.
Right.
But what if your data is encrypted and sharded across 1 million tiny servers that are constantly moving at 17,500 miles per hour? passing over international waters 90% of the time. Whose laws apply then?
It's the ultimate offshore data haven. The cloud would finally, literally, be in the clouds.
Precisely. The filing talks about data processing that doesn't sit on any specific country's soil. For now, anyway, this is the big vision. Hundreds of gigawatts of AI compute capacity hovering over all of our heads.
But we have to be the voice of reason here. The risk of Kessler syndrome from this just seems it's off the charts.
This is the part of the proposal that keeps space policy experts and astronomers awake at night.
For those who don't know, Kessler syndrome is the cascade effect, right? Debris from one collision hits another satellite, which creates more debris, which hits more satellites.
Until the entire orbital shell becomes a lethal shredder that's unusable for centuries.
Yes.
Right now, we are worried about the 5,000, maybe 8,000 active satellites in orbit, adding 1 million more objects, even if they're small.
It turns low Earth orbit into a minefield.
It changes the probability of a collision from unlikely but possible to statistically inevitable. And the astronomers, they're already filing emergency petitions with regulators. If something like this goes through, ground-based astronomy as we know it is basically over. The night sky will become a moving ceiling of artificial stars.
It really feels like we're at a crossroads. We are deciding right now whether Earth's orbit is a nature preserve to be studied or an industrial park to be exploited.
And all the economic momentum seems to be pushing heavily toward industrial park.
But even if they get permission to launch these million servers, there's another problem, a huge bottleneck. You can have the world's biggest supercomputer in space, but if you can't get the data down to my phone or my computer on the ground, it's basically useless.
You've hit on the ground segment problem, and for decades it has been the unsexy, unglamorous, and largely ignored part of the space industry.
We're still using big dishes, right?
We are still, for the most part, using giant parabolic dishes that have to physically, mechanically swivel to track a satellite as it flies overhead. They're slow, they're incredibly expensive to build and maintain, and they can only talk to one satellite at a time. It is literally 1960s technology trying to service a 2026 level infrastructure.
Okay, so who's solving this? Our research pointed to a company called Northwood Space, and I have to bring up the CEO because it's a genuine plot twist. Bridget Mendler,
Yes?
the former Disney Channel actress and singer, star of Good Luck Charlie, and now a space infrastructure CEO.
It is a fascinating career pivot, for sure. But let's be very clear. The tech and the business are absolutely serious. Our team noted they just closed a $100 million Series B funding round and, at the same time, book a $50 million contract with the Space Force. This is not a hobby.
So what's their tech? What are they building?
They're not building dishes. They are mass-producing phased array antennas.
Okay, break that down. How does a flat panel antenna track a moving object in the sky without any moving parts?
It's really clever. It uses the principle of constructive and destructive interference. So imagine you drop two pebbles into a calm pond. The ripples, the waves, interact with each other. A phased array is a flat panel with thousands of tiny little antennas. By minutely delaying the signals sent from different parts of that panel, by shifting the phase of the radio waves, you can get all those little waves to add up in one specific direction and cancel each other out in all the others.
So you're electronically steering the radio beam instead of physically moving a giant dish.
It's a digital spotlight instead of a mechanical flashlight. And because there are no moving parts, they can be ruggedized and mass-produced much more cheaply. Their whole business pitch is to make ground stations as common and as easy to install as cell phone towers. They want to be the Ethernet port for space.
So if SpaceX is building the giant server farm in the sky,
Northwood wants to build all the cables that plug that server farm into Earth. It's the classic selling shovels during a gold rush strategy.
and it seems like business is booming.
It is. And it also creates a much more resilient network. Instead of relying on one giant single point of failure ground station, you can have a distributed network of thousands of these smaller, cheaper panels.
It's incredible how the industry creates its own massive problems, like too many satellites to track, and then immediately pivots to fund the solutions to those problems.
That is the absolute definition of a high beta phase. The problems are scaling exponentially, but so are the solutions.
Okay, so we've got the rockets, we've got the orbital servers, and we have the ground stations to talk to them. But space itself, the environment of space, is still actively trying to kill all this expensive hardware. And this week, we learned a little more about how it tries to kill it and maybe how we can start to fight back.
This brings us to these smiling electrons.
I just love this name. It sounds like a 90s indie rock band. But it's actually a pretty significant physics discovery that was published on February 12th.
It is. A research team identified a new phenomenon happening in Earth's magnetosphere. That's our planet's magnetic shield. They were looking at a very specific area called the electron diffusion region.
And that's the spot where the solar wind from the sun first makes contact with our magnetic field, right?
That's the front line. The sun is constantly blasting a stream of charged particles at us. When that solar wind slams into Earth's magnetic field, the magnetic field lines can break and then violently reconnect. And that process releases a huge amount of energy.
So where does the smile come from?
The scientific visualization of the energy transfer patterns during one of these reconnection events. It literally looked like a smile. But what's important is what it tells us. It's a precursor. It's a sign that the shield is about to buckle and let in a burst of high-energy particles.
Okay, so why does the CEO of an orbital data center company care about smiling electrons?
They care because of something called a single event upset. A single high-energy particle from a solar storm can penetrate a satellite's shielding and flip a bit in a computer's memory from a 0 to a 1.
That could corrupt data.
It could corrupt data, or it could short-circuit a processor entirely. If you have 1,000,000 AI servers in orbit and a major solar storm hits them unprotected, you could lose the entire constellation, or worse, get subtly corrupted data across the entire cloud. Understanding these smiling electrons is like building a weather radar for space radiation.
It lets you see the storm front moving in.
Exactly. It could give you enough warning to put the satellites into a safe mode, shutting down the most sensitive electronics before the worst of the storm hits. It's fundamentally rewriting the weather map for space.
So we're getting better at mapping the weather, but our team also flagged an update on how we might be able to move much faster through that weather. Nuclear thermal propulsion, NTP.
This has been the holy grail for Mars missions for 60 years. And this week, NASA's Marshall Space Flight Center announced they completed a series of cold flow tests on a new nuclear engine design.
Cold flow means they didn't actually turn the nuclear reactor on, right? No fission was involved.
Correct. No nuclear reaction yet. Cold flow testing is when you run the propellant, in this case, super chilled liquid hydrogen, through all the engine's plumbing, the pumps, the turbines, and the nozzle, but without heating it up. You're just validating that the fluid dynamics work as designed.
And can you just remind everyone why a nuclear rocket is so much better than the chemical rockets we use today?
It all comes down to a metric called specific impulse, which is basically the rocket science version of fuel efficiency, or miles per gallon.
Higher is better.
Much better. In a chemical rocket, you get heat by burning two propellants together. In a nuclear thermal rocket, you use a compact nuclear reactor to superheat a single propellant, like hydrogen, to extreme temperatures. You get roughly twice the efficiency.
And what does that mean for a trip to Mars?
It means you can cut the travel time in half. Instead of the standard 7 to 9 month journey, you could potentially get there in 3 or 4 months.
That's a game changer. Less time in the harsh radiation environment of deep space.
Less time, less radiation exposure for the crew, fewer supplies needed, less psychological strain. It solves so many problems. And seeing real hardware go through these validation tests moves the concept from the realm of science fiction into serious engineering validation.
But even a faster trip, 3 or 4 months in deep space, that's still incredibly damaging to the human body. And that brings us to what might be the most fascinating biological breakthrough our team flagged this week. The youth protein.
DMPF1.
Yes. It's funny, we always focus on the rocket, the shiny hardware, but the fragile human inside is always the weakest link.
It really is. The biggest threat on a Mars mission isn't a rocket failure. It's galactic cosmic rays. These are heavy ions, particles from distant supernovae that are traveling at near the speed of light. They shred human DNA.
And they specifically damage the brain.
They do. They cause damage that looks remarkably like accelerated aging. Think rapid onset Alzheimer's or dementia.
Yeah.
There's a very real risk that the first astronauts could finally land on Mars, but be too cognitively impaired to perform the mission.
So you win the historic race to the red planet, but you can't remember how to open the airlock or what the mission objectives are.
It is a genuinely terrifying prospect. But this week, a research team published findings showing that by boosting the production of this protein, DMTF1, it can actually rejuvenate aging neural stem cells. It appears to effectively reverse some of the damage caused by radiation.
So are we talking about a pill? A gene therapy? What's the application here?
The research suggests it could be a gene therapy administered to astronauts before the flight. It would be like a biological radiation shield to go along with the physical shielding of the spacecraft. It turns the astronaut themselves into a more hardened piece of equipment.
It's just fascinating to me that the potential cure for aging on Earth might come from the research we're doing to survive travel in deep space.
It so often works that way. Pushing into these extreme environments forces us to solve the most fundamental biological problems. If we can figure out how to keep a human brain young in the radiation bath between Earth and Mars, we can almost certainly figure out how to help brains stay young right here.
So we've got the tech to get to space, maybe the tech to get there faster, and even the biology to survive the trip. Now, let's talk about what happens when things inevitably break. Because right now, if a satellite runs out of fuel or a component fails, it just becomes a piece of very expensive, very fast-moving junk. But that's starting to change.
We are witnessing the birth of the in-orbit service economy. And this week, we saw a really important joint mission between NASA and a commercial company called Momentus.
This is the mission with the Vigoride 7 vehicle and a little satellite called the R5S10. It honestly sounds like a droid from Star Wars.
It kind of does, and the mission is essentially a demonstration of a tow truck and an inspection robot for space. The little R5S10 is going to fly around the larger Vigoride vehicle, take detailed photographs of it, and then practice docking with it.
Now, this might sound a little trivial to some people. I mean, we've been docking spacecraft with the International Space Station for decades. Why is this a big deal?
Because docking with the ISS is what we call cooperative.
Mm.
The station is designed to be docked with. It has a beacon, its computers talk to your computers, it has a dedicated port. Docking with a dead, unresponsive satellite is non-cooperative. It's probably tumbling, it's silent, and it offers you absolutely no help.
It doesn't want to be caught.
Exactly.
Yep.
So if Momentus can prove they can safely approach and grab a tumbling, non-cooperative object, it means they can potentially refuel it, repair it with a robotic arm, or at the very least tow it out of the way into a safe graveyard orbit.
It completely changes the economics of satellites. You no longer have to throw away a $200 million satellite just because it ran out of $5 worth of fuel.
That's the business case in a nutshell. And this isn't happening in a vacuum. The UK also doubled down on this concept this week. They officially opened the DEEP Lab. That's the Disruptive Experimental Electric Propulsion Lab.
And what are they doing there?
They're building and testing the next generation of engines for these kinds of space tugs. Electric propulsion, like ion drives, is very low thrust, but incredibly fuel efficient. It's not great for getting off of Earth, but it's perfect for slowly and efficiently moving things around in orbit over long periods.
So we're building the infrastructure for gas stations and mechanics in the sky, but this brings up a huge question. Who is giving out the permission slips for all of this? I mean, if I want to open a hot dog stand on a street corner, I need a permit. If you want to launch 1 million satellites, surely you need a permit too.
You do. And the regulatory bodies like the FCC here in the U.S. are, well, they're panicking. They're trying to keep up. But to their credit, the FCC proposed a really radical change this week. It's a new proposal called Part 100.
Part 100, it sounds like a bad movie sequel.
It might not have a great name, but it's actually a potential revolution in government bureaucracy. They are proposing a new assembly line model for licensing satellites.
An assembly line for licenses, what does that even mean?
Right now, if a company wants to launch a constellation of, say, 1,000 identical satellites, they have to submit 1,000 nearly identical applications, and the FCC has to review every single one individually. It's a nightmare of paperwork that takes forever.
So what's the new model?
They want to move to a system of type certification, just like the FAA does for aircraft. If Boeing wants to make 1,000 737s, the government doesn't crash test every single plane that rolls off the assembly line. They certify the design. The Part 100 proposal would do the same for satellites, certify the system design once, and then the company is free to mass produce and launch them much faster.
That just makes so much sense. It's the government finally admitting that space is no longer a boutique artisan industry where every satellite is a unique masterpiece. It's mass manufacturing now.
It is their own high beta moment. The regulators are realizing that if they don't streamline their processes, the rockets will be sitting fully fueled on the launch pad, waiting for someone in an office to digitally sign a PDF. The technology is sprinting, and the law is trying to catch up.
Okay, so let's zoom out and try to tie all of this together. We started this conversation by calling this the High Beta Week. We've covered new heavy lifters from Europe and China, a wild proposal for 1 million satellite data center, new ground stations to talk to them, smiling electrons, nuclear engines, anti-aging proteins, and now space tow trucks and regulatory reform.
When you list it all out like that back to back, it really does drive the point home, doesn't it? This really felt like the week the sci-fi future became the industrial present.
It absolutely does. It feels like the entire global space industry just collectively woke up and decided to get deadly serious all at once.
And the risks are so much higher now. We talked about the debris risk, the traffic management problem, but the capabilities are also scaling at an exponential rate. What we're witnessing is the construction of a permanent, self-sustaining economy off-planet. It's not just about exploration anymore. It's about commerce.
And that leads me to a final thought that's been rattling around in my head ever since we started digging into that SpaceX orbital data center proposal.
Let's hear it.
Well, if the bulk of the world's computing power moves to space, which this proposal suggests, and eventually, with things like space-based solar power beaming, the bulk of energy generation moves to space. And then mining for raw materials moves to asteroids or the moon. Does the Earth economy eventually just become a subsidiary of the space economy?
That is a very provocative thought.
At what point does the most valuable real estate stop being on the ground? At what point does Earth just become the, I don't know, the quiet residential district of the solar system while the factories and the data centers and the banks are in orbit?
It's a valid and fascinating question. If the centers of growth, the sources of energy, and the hubs of data all move up there, then the entire economic center of gravity for humanity lifts right off the surface of the planet. We might be watching the very beginning of that transition happen right now, this very week.
So the most valuable real estate in the solar system might not be in Manhattan or Tokyo anymore.
It might be a plot of vacuum at an orbital inclination of 53 degrees.
A lot to think about. We would love to hear your thoughts on this, whether you're on YouTube or your favorite podcast app. Leave a comment and let us know what you think about the idea of 1,000,000 flying data centers. Is it the future of AI, or is it a sky full of junk?
We really do read all the comments,
Yeah.
and we love the debate, so please let us know.
Thanks for joining us on Tomorrow Unveiled.
See you in the future.